Hello, hello. So we have a talk that was unannounced in the beginning, and we're going to talk a bit about benchmarks and how to measure performance. We work on PyPy for quite a few years, so we've seen tons of code, both open source and not, where people do various things and write various benchmarks and then claim various things about performance of their either programs or virtual machines. So we're gonna explain first how CPython and PyPy run programs, like just enough to understand the performance implications, and a bit of theory, how to measure performance in terms of statistics, show microbenchmarks and why they're not that great for most purposes, and then talk a little how you should, or well, I don't know, how you should approach writing real-world benchmarks of your applications. So first, CPython. CPython is called a simple virtual machine. There's nothing simple about CPython, but the basics are kind of easy. So it compiles Python code to bytecodes, which is like a classic part of compiler that you probably have seen at the varsity. Then runs the bytecode in a loop, and then usually invokes tons of runtime functions written in C. So let's have a look. Hello? Work? Hello? Let's try like this. So we run Python, and we write a simple function which will do something like add two numbers. Okay? So if I call the function 2 and 3, it will return 5. So there's a module called this, and this will happily unpack the function and show the bytecodes. So this function is particularly easy. It does load fast, which takes the local variable, number 0, in this case it's A, and loads it onto the virtual machine stack. Then it does the same with local variable number 1, which is B, then calls binary add with no argument. Binary add takes two items from the stack, adds them, and puts the return value on the stack back again, and return value returns the function. So an important part here is that load fast doesn't talk about types. It's not load int, it's not load string. The function will work happily with ints, and you can call it with A and B. It does string concatenation. You can call it even with A and 2, and then it crashes. So load fast really takes an object of any type and puts it on the stack. Then binary add has to dispatch based on the first type, and then based on which functions it will call, based on the type, it will call a specific function in C for adding, say, integer to integer or string to string. Or if there is a missing function, it will call a function that raises type error. How exactly addition works in Python? We once tried to write a slide about it, and it doesn't fit on one slide in any reasonable font. Tons and tons of cases what happens if you have a subclass of this but not a subclass of Unicode. It's quite complicated. What does PyPy do? PyPy is not so simple virtual machine. It does all of the previous slide. And then if the loop or function is called often enough, do you remember the numbers? It was 1031, I think, times, which is a nice prime number. And then you compile the loop into optimized assembler. And then assembler can contain all the logic, or sometimes you'll still call the runtime for something. So I wrote a simple function. It's not a very useful function, I must admit. It counts numbers. up to some large number. So if I do this, why am I not in the correct directory? If I say, it takes a bit forever. Okay, I got it. And I do the same thing with this. A function is called f. It has a bit of stuff. Most of the stuff is as I've seen, except a few constructs. So load const will do the same as with variable, except we'll load a constant. And setup loop does something, I don't know. Sets up the loop. Hello. This is a conditional jump. This is also a jump. And in place add is plus equals instead of just a plus. The idea is that you have a loop here, so jump absolute 9 here, will jump hop here to the number 9. So this bytecode is a bit hard to follow, but it's very simple. Like the mapping from Python source code to this bytecode is most of the time very trivial. Like the Python compiler doesn't do any sort of advanced analysis. Like yes, it will constant fold 2 plus 3, but that's about it. Like this is as much optimizations as it really does. So really what CPython does is have a giant loop that dispatches based on this bytecode and calls C functions based on this on the implementation of the bytecode. Now let's run this with Ooh, what is it? What's going on? Let's run this with PyPy. So I have a PyPy virtual env. Well, that just runs PyPy, and I'll run a magic command. And this is a compiled function. If you look at it, it contains, this is the Python bytecode. This is the source code. This is the Python bytecode, which is load fast, load const, and compare up. And those are operations that are compiled by the JIT. They're like low-level operations. If I show the assembler, it's really C-level operations. So CMP is a comparison, and JGE, they have awesome names most of the time. This is a jump greater equal, and then the jump is to some assembler code that lives somewhere else. Then in place add does really, this is effective address load or something. It's an optimization that works on x86 very well. It adds one number essentially, and then this guy is a jump if the signal has been produced. Because Python has to nicely report you keyboard interrupt in case you press Ctrl C. This is kind of important that this simple loop is 1, 2, 3, 4, 5, 6, 7, 8 assembler instructions. That's a bit more than a C would produce, but not more by much. I have a slightly more complicated example here, which does it just calls str on consecutive integers and then length on the resulting string. So if I run that one with a similar magic command, takes a bit longer. Yes. So this is more or less the same function, except here you can see this is a call, which if you unfold the assembler, it's quite a few instructions which are necessary for the x86 ABI. But at the end, it calls a piece of runtime that converts integer to string. So this is how compiled PyPy code runs. And the trick part is that you don't compile this immediately as you encounter a function. You really have to wait a bit, run in the interpreter, and then run the and then compile and run the resulting assembler. Ooh, crash. Okay, so this was like the basics, how the compilers that we happen to have here run. Now let's talk about the ideas about measurements. So you run your benchmark, you can run it once and measure the time. That's not good enough. You're gonna do the distribution should be Gaussian, which means you get an average, and then it will vary one way or another depending on the complexity, depending on various statistical properties. You take the average, then you compute the variation, which is like how broadly it distributes. And then if the variation is too large, you just increase the number and you should be good. So I had to load the Gaussian distribution from the matplotlib examples because it was really hard to get it in real life. I'll show you why. This is how it should look like. So the middle is where the majority of cases land, and then sides are like outliers. Okay, let's do it. So, because everybody loves Fibonacci, I'm gonna write Fibonacci. I'm gonna just copy paste stuff here into a file so I don't have to write it. So, recursive Fibonacci looks like this. It's 1 for 0, 1, and otherwise you just call the n-1 and n-2 recursively. And then I'm gonna run it in the most easy way possible, which is compute the Fibonacci number of 17, then run it 1,000 times, and then take all the numbers. So say if I print times here, I'm gonna run it with normal Python. Fib2. Bunch. I get a bunch of numbers. Those numbers look roughly the same. Good. So I'm gonna take the histogram, put it in 20 different buckets. Oh, I need to import NumPy. Up and plot the histogram. The bins are, there's one more bin than histograms, because those are just boundaries. Okay, fair enough. Didn't do anything. Yes, matplotlib and awesome APIs. Okay, so how does it look to you? To me, it doesn't look like this at all. Huh? What's going on? Why? What did we get here? We got sort of half of the Gaussian distribution. It will still be a bit of a stretch. So maybe taking average is not good enough. Okay, fine. I'm gonna plot the times one by one. So I'm just gonna take this guy and plot the array of times. What is it? I was supposed to get like average here, or like in the middle, and then up and down, up and down, up and down. Why did I get that? What is this, for example? So the answer is most of the time you don't know. It's can be CPU doing other stuff, but most of the time it's your program doing other stuff. So Python programs are doing a lot of work even if they don't look like that. So each time you run it, there's some overhead that's distributed across multiple runs. It can be GC collect, it can be various things that just happen, or like cache misses or whatever that happen every now and then. Now if you take the average, you're gonna land here, and the average, maybe it's telling you something, but it's definitely not Gaussian distribution. Okay, so what people do, they take the minimum. But the minimum is really not good enough, because you get those peaks that if you average over all of them, those effects are really important, even if you even if they don't show up, it never runs. So taking minimum is no. So what we do, we still take average, but the mathematical model behind it is even worse than we thought. Okay, so well, the main problem with the previous slide is that it's a bunch of nonsense. It's not true at all. Solution is you try your best and do the average anyway. Maybe you can cut off the warm-up time. I didn't show you the warm-up time. So say we run the same thing with PyPy. And will not run because we don't have matplotlib, but hey, we have hacks. So the hack is here. The hack is not imported. Okay, so what's here? If you look here, you see that the times actually jump quite a lot. Like the first peak, which is 1 pixel wide, it's really all the way almost there. Then jumps here quite a lot, and then does this. And that essentially means that this is when JIT kicks in, tries to compile stuff, and maybe it compiles, maybe it fails, but it takes a lot of time, and then it runs more or less smoothly until the next JIT or GC or whatever kicks in. So you have large peaks that are a lot larger than CPython, and this is just too short. It's not long enough to be really smooth. It should be really smooth after all the JIT is warmed up. So you get a giant warm-up time, and then if you want to account for way PyPy works, depending whether you care about warm-up or not, you can cut the first part and see, okay, I have a long-running server. I really don't care if the first request is long or first 1,000 requests. I'm gonna just cut off the warm-up time. It really depends what you're trying to do. The solution is not ideal at all, which is a bit of a problem, but this is the best we can do, I think. I mean, if somebody can come up with a better mathematical model, I would be very happy to help with that. Okay, Armin, your turn.
Okay. So I'm going to talk to you about an alternative, writing benchmarks. Well, when you are about to write benchmarks, sometimes you want to actually not test a whole big program, but you want to test how fast is it to do this single thing. So typically you write a micro benchmark. So here are two examples of micro benchmark. You have the recursive Fibonacci that Maciej just showed. You have another one that is kind of standard in Python that's called PyBench. But then, well, let's look. Let's look how PyBench looks like. So yes, PyBench is a bunch of benchmarks that all look like this. This is completely artificial code. I mean, here in the loop, what is it doing? Nothing, basically. It's just computing how much time it takes to create instances of C and D and E. Okay, and the loop does nothing. That's why here it's printed in red because of Maciej's advanced editor modes that notice that it's assigned to a local variable, but then it doesn't go anywhere. So yes, so we can run it on top of CPython. Yes, on top of CPython, it will actually check how much time is spent to create your instance and call the constructors. But then if we try to do the same thing on PyPy, this is what occurs. This is the compiled. So here you see the loop. You see all the Python level calls to constructors. You see all the bytecodes. And if you look very carefully, you can see things like force token, which is all that is left. Yes, this is a great example. Here you have a call to a constructor. Constructor will assign these three variables. So well, to do so it needs to do all these bytecodes, okay? But there is nothing left in terms of assembler produced because, well, because in this example, PyPy is able to know, okay, here I'm creating an instance, but okay, I'm going to delay a bit the creation of the instance because you actually have in real code some case where you create an instance, then 2 lines later you read its attribute and then you forget the instance. So PyPy optimizes this by not creating the instance. So here it's exactly what it's doing. So basically, if you run this particular micro benchmarks on PyPy, you're benchmarking an empty loop. So this comment applies to most micro benchmarks actually. It's exactly like I want to measure how slow or how fast in C it is to call an empty function. How do you do that? If you are measuring the speed of an optimizing compiler, then it does not make any sense because all the call to empty functions will be inline and won't do anything at all. So yes. So okay. So well. So yes. As a summary, this kind of micro benchmark don't make sense in any real optimizing framework like GCC or like PyPy. So what you need to measure is real programs that really do something, obviously. So this is another example that actually is only about CPython. Between CPython 2.6 and CPython 2.7, there was a small minor change hidden somewhere in the change log, and it's about something about the garbage collector, so cycle detector of CPython. Okay, it was just a detail, but no, actually it was not, because on a real example, I mean we have well. We have a program that we use a lot that was a really long running program. It took 3 hours on Python 2.6 and only 1 hour on Python 2.7, just because of that change. So it has actually a huge effect on some examples, and particularly on very large program. So it's well, the point is that it's impossible to write a micro benchmark for it. Unless, well, you can if you really target exactly the problem that was solved, but any general purpose micro benchmark will not show any difference for this case. So yes, these are the problems that we run into when we are talking about PyPy is fast. And then you have some other guys that post a blog post and say, well, I measured this thing and I found it not to be very fast. And this thing is usually some kind of complete macro benchmark. So it does not have any practical relationship. I mean, yes, I mean I don't know why, but it seems to be recursive Fibonacci's favorite example. So for a long while we did not perform well at all on recursive Fibonacci because we did not perform well at all on recursive function, because, well, that's not very common in Python. I'm not saying it does not exist, but I'm just saying it's not the most common construct. Well, nowadays, if you actually take a PyPy, then it's very fast on recursive Fibonacci too. Yes, good. So yes, well, here I'm bashing against microbenchmark, but what kind of benchmark actually makes sense in a context like, for example, PyPy? Well, we actually have a suite of benchmarks. It contains various kinds of benchmarks, from very large to very small. The point is that all of these benchmarks are actually real life code, like computing something that we can measure. And well, yes. Also, it does not make sense to write a macro benchmark testing only one feature, but then it makes sense to write benchmarks that are a bit targeted. Like you want to check how much time is spent, for example, in these programs that use large, long numbers, or how much time is spent on that other program doing input-output, for example. Yes, the case of input-output is one case where we don't actually have very much benchmarks so far. Like it's one of the things that we are working on to improve in PyPy. So yes, so as a summary, if you want to write benchmarks, well, the first obvious thing is to measure what you are interested in, but well, derive macro benchmarks from your bottleneck, but be skeptical about them, as in you really need to write code that computes something and get you a result. So, well, the general answer is the general comment is to understand what you are measuring, obviously. Yes. So thank you. This was. Here you see some URLs about PyPy more specifically. Yes. Now we are taking questions.
I have a question about this list of times that you have showed with PyLab. You said that taking average is not the best approach, taking minimum is not the best approach. Did you think about taking median from it?
It has all the same problems. Like, we lack a decent mathematical model what is going on. So, I mean, we still take average, really. But you need to understand the limitations of what you're doing. Maybe the average on the long enough run is something that you're mostly interested in, but it has limitations because the way you run it does not adhere to the classic statistical model. So yes, you take average, but understand the limitations of what you're doing.
Hi guys, thanks for the talk. I was wondering, you've mentioned that between Python 2.6 and 2.7 there were not that many optimization differences in the changelog. What are the chances that some of your experiments from PyPy will land in the CPython? Are there any chances, or for at least some of those changes, to improve the CPython itself?
So the simple stuff landed in CPython, like the method cache, maybe not, but like, yes, method cache and a bunch of stuff. The main problem is that a lot of PyPy optimizations rely on having a just-in-time compiler. Like, yes, you can constant fold away things, but only if you happen to compile it dynamically. So unless CPython grows a a lot of optimizations are really not going to make any difference. Like, for example, maps. We use maps for object access. So instead of dispatching on a dictionary of attributes, you dispatch on the dictionary on the type, and then you look up the index in the list. And the first part, if you know the type statically, the first part you can constant fold away. So there's no dictionary overhead lookup for instances at all in PyPy. But you need a just-in-time compiler for most of the optimizations. I can see.
Well, I should add that the map thing was actually ported into Python 3 point something, because it does not have any speed effect, but it has memory saving effect.
Yes. Okay, but the yes, you essentially, I can see some stuff where you dynamically compile bytecode. You don't necessarily need to emit assembler and specialize this, but it's usually above the threshold of which CPython wants to complicate things. I mean, I completely don't understand their policy at all, because they can write very smart C code this here to optimize this tuple creation by 5%. Yes, but they are not willing to take any complications on a higher level. So I think no, for reasons that I don't completely understand.
So further question is, what are the chances for kind of like a JIT solution in the CPython itself? You've proven with PyPy that it helps a lot. What you've mentioned, that the core devs of the CPython, they do spend a lot of time fixing here and there because it will improve performance. I know that Raymond and all the iter tools and all the algorithms he's taking care of are quite good if you measure the performance. But again, this is written either in Python or in C, but it generally doesn't help the overall Python experience to be better. So I know that I've seen your lots of posts on Python dev. Are there any chances that you'd be forcing to introduce JIT into CPython?
Hello. So one problem is that Armin tried and failed, which is a bit of a problem. Armin wrote Psycho at some point, and Psycho kind of worked, but it will. At some point, you're hitting limitations in CPython model, like ref counting and the CPython extension modules, which you're not allowed to change API. That introducing a JIT to CPython is harder than writing the JIT for Python from scratch, which is already hard. So yes, maybe if someone has enough, but someone has to do it at the end. Like the Python dev core team is way more interested in discussing endlessly how to name a keyword argument. So yes, someone has to do it. Someone with a slightly different approach to Python dev, which doesn't mean it won't happen, but I just don't see it happen anytime soon. And it takes usually years for such a platform to develop and mature, because then you're running into problems, into bugs, and how do you approach things? At the end of the day, it won't be faster than PyPy because, say, they can't change the garbage collection strategy, or they can't do this, or they can't change the C API to something that makes more sense for a new optimized version, and stuff like this. So yes, it's possible, but it's a very thankless job to do.
Hi, I would like to address once more this question about the average, because you said that it's a problem to formulate a mathematical model for this. Okay, I'm not going to go into details. Maybe there is some stochastical model, things like that. But what about the average, the weighted average? Because if your pattern of the high peaks is reproducible, you can weight it by the frequency, for example. Have you tried something? Have you thought about this? Or it is not reproducible at all?
A bit of both. Yes, it's mostly reproducible, but not always. It depends on details. And why would you care about why do you want to add more or less weight to the peaks? Because at the end of the day, maybe you're interested in the overall program performance, or like it really depends on what you're looking after. Like I don't know. I would love to see a simple paper that explains the model and like get some assumptions. I just didn't happen to run into one.
So I think that you just, well, what you said just now is that you just don't have enough information about what people are using PyPy for and what people who are using PyPy actually need, right? Because you don't know what optimize, because you don't know what they want, right? Well, obviously it would be better if it was all faster, but you don't know specifically which parts they want. If it's okay for them to have long startup, long warm-up time, or if you should also include the warm-up time in your statistics and so on. Maybe you should have some use cases and I don't know. Yeah.
So
like different actors in your model and different people using them.
So I write open source, but I'm practical about it. I'm willing to exchange optimizations for money or for blog posts describing how they use PyPy. So in general, if people are willing to pay money for certain optimizations, we're generally happy to do them.
Like a great approach.
Okay. Are your benchmarks available online?
Yes, they're. So the main benchmark website is here. Benchmarks, plural.
Oops.
Yeah. bucket. Benchmarks.
Well, you can find also this page if you just go to speed.pypy.org.
Yes, that too. Okay, fine.
So speed.pypy.org is this set of benchmark run nightly on PyPy.
Awesome.
And you find some link.
What hardware do you use?
Sorry?
What hardware do you
Of
use?
course, just standard. I mean, it is actually a server, a smallish server provided by some company.
I think it's an old Xeon mostly. Like, we don't run benchmarks on ARM because ARMs are way too slow to finish in one night. But we run them on like a standard 2 or 3 year old, no, maybe even older Xeon server somewhere. Yeah, that's pretty much it. Like, we would ideally run it on a variety of hardware, especially because the cache size makes a lot of difference in the benchmark run. But yes, we just happen to have a server that's mostly dedicated to benchmarks. Yes, it's something like, yeah, whatever that means. Some on Xeon.
Okay, thanks.
Okay, this may be a basic question about PyPy, but there's this issue with the startup time where JIT has to warm up and compile the often used areas of code. Does PyPy do, or is it gonna do? Is it gonna store some data between runs so that subsequent runs of the same scripts are faster? Because if you run the same code in a tight loop, but in between runs, well, you execute the script often, not run a tight loop. You have to store data on disk to optimize it. So does PyPy do that?
So I'm gonna answer in 2 parts. First part is you can change your program to a daemon simply by having a command line interface just talks to a daemon, which is most of the time not that hard. And the second answer is, if you can tell me that the class you loaded from an import system in Python is the same as the class loaded from the previous one, like really the same, then I'm willing to do that optimization. But I didn't find a way to decide, like, is it the same class? Because import machinery in Python is absolutely crazy. It does things, and you can read the class definition from a socket if you want to. How do you detect that, essentially? Because the source code is by far not enough. If the source code is identical, that doesn't mean anything, because there are constants. How do you compare constants? Well, integers are easy to compare, but sometimes the constants are more complex than the integers. Are they the same? How do you hash them? Where do you take this info from? So I guess the answer is no, unless you can somehow trick the Python machinery to give you always the same stuff, like really the same stuff. So after runtime initialization of a class, you receive at the same stage.
Okay, so many more questions.
Did you think about, I know this is a kind of a bad idea to make your own language, but make your own language like Python, but without all the dynamic problems of optimizing Python.
So the dynamic part is not the problem anymore. We solved that problem. Now,
Right.
if you want to make a better language than Python, you're welcome to use our toolchain, which is what we are working on. And we are really more language implementers than language designers. Like, we really like working on various parts and optimizing it. So yes, make a different language and give us challenges how to optimize that. And people do it constantly. People write, I don't know, what is Timothy working? Clojure or something else?
The thing is, you have enormous knowledge about what's good, what optimizes well.
So my opinion is that you should not write language, like design a language that's easy to optimize, because then you end up with C++. Yes, C++ is easy to optimize, but it's really hard to write in. I want languages that are easy to write, and then somebody else, like us, can deal with optimizing them. That's
Okay, but sometimes you do stupid things that are like don't improve readability at all, or don't improve how easy it is to use, but have a great impact on how easy it is to implement it, right?
Yeah.
Sometimes you do stupid things just because you don't know.
Yes, but those are minor. Like the major parts are really a trade-off between the ease of implementation and the ease of usage. And yes, on one side of things, you have Python, which is hard to optimize, but easy to write in. On the other side is C++, which is really easy to optimize, but really hard to work with. And so I'm leaning towards the side of use. I'm too stupid to use C++, for example.
Okay, thank you.
Okay, if there are no more questions, then thank you.